about dynamic graphs, in particular doing machine learning on dynamic graphs. And the model we proposed in a paper a while back called Temporal Graph Networks. And this is work done in collaboration with my colleagues at Twitter. So first of all, a little bit of background. So I mean, I think here everybody is pretty familiar with graphs, but as we know, graphs can be used to model very nicely many different phenomena and systems, so social networks, molecules, functional networks of the brain, interaction networks, and many more. No need to spend that much time on that. I'm sure you're all familiar. And we also know that we have this very powerful tool to learn on graphs, graph neural networks. So you've been hearing all days about them. There are many ways to look at them. One common way is the message passing framework, where you compute messages between neighbors, and you exchange the messages, and you update representation of nodes by aggregating this message from their neighborhood. However, it turns out there is a little bit of a problem, and the problem is that many graphs are dynamic. By dynamic, I mean that they clearly, naturally evolve over time, appear over time, and so here we have a couple of examples. So clearly, forgive me, today I'm gonna draw heavy inspirations from Twitter and the graph. We have a Twitter. There are many other possible examples, but I spend, I guess, most of my time thinking about these applications. So on one side, you have social networks. Here we have users. They follow each other, and these follow actions happen at a particular point in time. And we are specifying these timestamps on the edges, and then we want to ask the question, maybe, is there going to be an edge between these two users at some future point in time? And here, what is crucial to understanding is that the timing information on the edges is very important and informative for the task we want to achieve. Because, for instance, the interest of people and their social circles is going to change over time. Or the interest may be seasonal and maybe depending on many factors. So knowing exactly when things happen is many times is crucial. Another examples is interaction networks. So here again, Twitter, you have users interacting with tweets. There can be many interactions, so like, retweet, reply, and so on. And all these things happen at a specific time. And again, we want to ask question of whether there's going to be another. Whether a user is gonna like a specific tweet in the future, or you can ask even many other different kind of questions. So from the research point of view, I guess there are at least two very interesting questions. And the first one is, again, how to exploit this timing information, this additional timing information, to generate better representation of nodes than if we didn't have this information. So we want to make use of this timing information. And this talk is mainly going to focus on this first part, and our paper did focus on this first part. Another very interesting question, though, is also to predict when things will happen and how things will change in the future. So, for instance, when will two given users interact again next, or which users will interact with a given tweet in the next hour. So maybe, so far I've been drawing a bit of too simplistic story. So it turns out there is a whole spectrum of dynamic graphs, going from less general to more general. So, I mean, the less general case is when we don't have time at all. So it's just our classic static graph. There is no notion of time, and so we just represent the graph as basically a set of vertices, a set of edges, and some edge feature, some node features, and maybe you can also have edge features if you want. If we, possibly the simpler generalization of this is usually called spatio-temporal graph, which is a graph which evolves over time, but not the topology of the graph. So the graph itself is actually fixed. What changes is features on the graph. And these changes are usually at regular intervals. So a classic example is basically traffic and traffic forecasting, where your graph is basically the connection of the roads. And this is clearly fixed because it doesn't change very frequently. And however, let's say every 10 minutes, you may observe some quantities on the road. So for instance, you may observe how many cars there are in a given road. And then you want to predict in the future, at some given point in the future, how many cars there will be. So this is kind of very similar to a time series scenario just happening on a graph. A bit of a generalization of this is what is called discrete time dynamic graphs. And in this case, also the topology of the graph is allowed to change. So for instance, we're going to have new nodes, new edges appearing or disappearing. However, this is observed also regular intervals. So you can imagine that we may have an underlying system, and only every hour we kind of observe the system, and we say the state of the system. So we usually, there are many of these scenarios, and we don't know we don't know what happened between T0 and T1. We just know the state at T1. So this is usually represented as a sequence of snapshots of the graph, and clearly also the features can change. And then there is the most general and also richer representation, which is continuous time dynamic graphs, which is basically where anything can happen at any time. So we allow changes in both the graph and the features, and also these changes can happen at any point in time. This is why it's called continuous time, and it can also be seen as kind of an irregular time series because the distance between events is not the same. And this is, you can see how this happens very often as many applications. So everything that happens in social network is of this kind, because you don't know when somebody's going to message somebody else. You don't know when I'm going to write a tweet. You don't know also in transaction networks, is another examples. Transactions can happen at any point in time. So really, this is the most general formulation, and is represented as a sequence of events, where each event has a particular timestamp. And we're going to see in a second what these events can be. So as I was saying, there are many types of events. And here there is a table kind of showing what they are. So we have what we call creation, and can be, if it's the creation of a node, the example is, a user that joins your platform, a user that joins Twitter, let's say. Creation of an edge would be, for instance, a follow edge, a user following another user. And clearly, it can be also both deletion and of both nodes and edges when somebody leaves or somebody unfollows somebody else. And we can also have feature changes. So a node feature change is, for instance, a user updating their bio, and an edge feature change would be, for instance, if a user was able to change their retweet message, even though we know that is not possible yet. But then an interesting question can be, okay, we have dynamic graphs. They appear in very often, and there are many applications. But why are they different? Why can't we just use the standard GNNs to model dynamic graph? Well, and the reasons are several. So first of all, we need to handle different type of events. So we have this creation, deletions, changes, which is not clear, how to handle them with the GNN. And also we want to use the timing of this information. We were saying before how the timing can be very important. Moreover, we want to be able to efficiently and incrementally incorporate new events. So if you think, you want to deploy a model like this, and then when there are new changes in your graph, in online changes, you don't want every time to, have to recompute everything from scratch, but you just want to make small changes to your, let's say, node embeddings. And this clearly, with a GNN, it's not clear how to do this. You would have to kind of rerun the GNN every time, for instance, a new edge is up. And also, you may want to do different tasks which are not normally handled by GNN. So predicting when something will happen is not a task usually GNN are seen, doing. So basically, if we use a static GNN, we would have a loss of information because we would need, for instance, to only work on a snapshot of the graph, but not the full evolution. So we wouldn't know, how we got there, but we're just seeing the last snapshot. And also, we will have a lot of inefficiency since we have this repeated computation, since the GNN is not able to incrementally incorporate new events. And also we would know how to do time prediction, so predicting when things will happen. So this leads me to the model. And so first of all, how does a temporal graph model look like in general if we want to work with temporal or dynamic graphs? And basically, I think the same way static genets can be seen as an encoder-decoder framework, I think it's very useful to see also a dynamic graph model as an encoder-decoder framework, where our input is still a graph up to some time t, where this is it can change. And this is represented basically as a sequence of as an ordered sequence of events, and we're going to have an encoder which is going to generate node embeddings, temporal node embeddings, because they depend on the time t. And then given these embeddings, we will have a task specific decoder, which for instance is going to do node classification, or it can do edge prediction, or depending on the task is going to be a different decoder. So we now want to create a model for dynamic graphs, for temporal graphs. So first of all, for this presentation, we're going to make a small simplification. So we're going to assume that our events are only going to be edge creation events, which makes life a bit easier, even though differently from previous methods, our TGN model is actually able to handle all the previous all the events that I've shown you previously, thanks to its very general framework. So yeah, we have our graph, which is a sequence of events, timed events. So this tuple just means there is an interaction, an edge, a new edge between U and U1 and B1 at time T1 with features E1. So very simple. So the first idea that somebody could have, and it was also kind of the idea behind a couple of previous papers, was well, this is a sequence. What should we use with sequences? Usually RNN work very well. Also, I guess it was before transformer became super popular, but also there are a bit of differences here from standard sequences that probably make RNN still a good choice. However, as I was saying, is a bit of a special sequence, and the difference that we need to have is that we need an hidden state for each node. So not just one hidden state for the sequence as you usually have, but one for each node. And then given a new interaction, what we do is we update the hidden state of the two nodes involved. So here I'm showing only one, but it will be for both the source and destination. And the way we update this new hidden state, so the hidden state for our node U at the time step I, it's going to be basically an RNN, which takes as the previous hidden state, and also takes what we call a message. And the message is basically containing the information of the interaction. So in this case, actually here there's a typo, should be M here, sorry. In this case is the concatenation of the hidden state of the other node and the edge features. So this contains everything you need to know about the interaction. And here we are saying, okay, update the hidden state of U based on this new interaction, on the information of this new interaction. And this gives you, a vector, an hidden state for each node. And these hidden states can be used as your node embeddings, as your temporal node embeddings. So the pro of this method, it has this built-in bias of sequentiality. So we know these events happen in order. So it's good to take that into account. However, the cons is that it's not really a GNN and is not really using the graph directly. So it may lose a bit of expressivity because of that. And also, this kind of suffers from the memory stillness problem. And now I have to tell you what the memory stillness problem is. So the memory stillness problem is the idea that if you look at these equations, it turns out that the hidden state, the representation of a node, is only updated when the node is involved in an interaction. Which means, if again we take Twitter as an example, if I'm away from Twitter for 6 months, I'm not going to have any, let's say I'm not going to have any interaction, then my representation is not going to be updated. However, that doesn't mean in the last 6 months, my interests haven't changed. It may just mean that, I didn't want to use Twitter. Then if I come back, now my representation is going to be completely outdated, meaning maybe bad recommendation. However, we can do better, and we will see later how to solve this problem. And another idea that you also have, and this was presented in another paper, was, okay, let's actually use a GNN on the graph of interactions, up to our time t. In particular, they use a GNN with attention and using the timestamps as edge features. What's nice about these is that attention can then, be done on the timestamps, and so hopefully you can learn patterns about maybe if whether recency is important or whether it's a seasonality pattern and this kind of things. So the pros are clearly that this is more efficient because there is no need for sequential processing that you have in RNNs. So this is going to run much faster. However, and also we're using the graph explicitly. So these, for instance, this mitigates the stillness problem. And this is because even though you may not have been active on Twitter, your friends may have been active. And so possibly if you have been off the platform for 6 months, but they've been engaging with content, if your interests have changed a lot, probably also your friends' interests have changed, and maybe we can infer that from what your friends have been up to using the graph. However, the cons is that this can only really handle edge addition events. So if an edge is deleted, again, not clear how to handle that, apart from just not having the edge altogether. And also, other types of events are not clearly handled. And also, this is not very suitable to line updates because you just have a GNN, and every new edge, for instance, you would need to run everything the GNN from scratch to update your representations. So the equation for this can kind of be seen as, we want the embeddings for all the nodes, and this is basically some sort of graph attention. And on the graph, on the features, on the edges, and on the features of the nodes. And this graph is given by the edge that are created in your list. So now we come to basically our model, temporal graph network, which tries to take the best of both worlds, while also being more general, and so defining a general framework that can allow, basically is able to handle all different types of events. In particular, the idea is we want each event to generate a message, and then this message is going to be used to update node representation. And on top of that, we're also going to use a GNN on the graph of interactions, which uses both these representations, which we obtain sequentially with an RNN, and also node features. So again, it's a very general alternative framework made up of 5 different modules, and is a generalization of the previously proposed models, so Jari, TGAT, and Direct. And I mean, here we have a very high level overview of what, again, our TGN encoder is doing. So we have this temporal graph, we fit into TGN, is going to give us embedding for all nodes. Here we're just showing 2 of them. In particular, we ask for embedding a specific time T8 because we want to kind of predict this edge, which was not given as input. And then we're going to have a decoder, which is an MLP, which takes as input the concatenation of these 2 embeddings, and is going to predict the probability of there being an edge between 2 and 4 at this time T8. So let's now look a little bit into in more details at what TGN is actually doing. And we're going to look at the different modules of TGN. So the first one is what we call the memory module, which is basically just the collection of hidden states for all nodes. So the memory is basically the same thing as the hidden state, and it is really what it is a vector for each node the model has seen so far. And it is a compressed representation of everything, of all the past interaction, but really all the past events that a node has been involved in so far. And important to note is that this is not a parameter, so it can also be updated at test time. And we initialize it at 0, and it can easily, this way it can easily handle new nodes. because when a new node appears that we haven't seen yet, we can just add a new vector of zeros to our memory and then start modifying it as soon as we see events for that node. Another, the following module is the message function, which is really, as I was saying, each event generates a message. And the message function is basically the function that creates that message. And then the messages will be used to update the memory. So for instance, given an interaction UV at time t with features E, we compute messages for both the source and destination. So this is similar to what we're doing what we have seen previously, but more general. And so we compute this message for both U and V. Basically, we define this as a very general function. In our implementation, it's either just a concatenation of the inputs or an MLP on the concatenation of the inputs. But it can be, depending on your application, it can be different things. And it's a function of the previous memories of the two nodes, U and V, of the timestamp, and of the edge features. So these kind of should summarize what happened in the event, so that we can update the representation, the memory of the node involved in that event. So then we come to the memory updater, which is actually the function used to update the memory. So this is quite simple. So our new memory for node U at time t is going to be this memory function of the previous memory and the message. So this is, in practice, this is an RNN. We use a GRU in our experiments. And basically, we update the memory using the message. This is all there is here. And then the last module is the graph embedding, which is kind of adding a GNN over what we have so far. So far, we have a memory vector for each node, which is, as we said, a compressed representation of the node. And now we really want to do a GNN over the graph that we have so far, using also the memory as sort of additional features. So we use the memory to really, nicely compress what has been seen so far. And then we do a GNN on this graph using also the memory and the node features. And this helps us to solve the stillness problem, which, as I said before, is the memory becoming out of date. And an example here is, the equation here is similar to what I shown before, only that we're doing this graph attention, also making use of the memory, which is computed by the other modules. Also, importantly, this memory now is more general and is able to be updated from any sort of event, not only new edge addition. So here is, just a picture that if we want to compute the representation for node 1, we're gonna use a graph attention network over its neighbors that we've seen so far, using both these are the node features, and this is the node memory that we're computed using the other modules. So let's look a little bit at what it looks like to do link prediction with TGN. Even though there are many different tasks, for instance, dynamic node classification, predicting future links, but also possibly classifying the whole graph over time. I'm going to look a little bit at link prediction. And what is interesting is that basically, clearly, we want the split of the data to be chronological. So if the data spans 1 year, one option is to do the first 10 months are going to be training, 11th month validation, and 12th month the test set. And the model wants to predict events, interactions, events sequentially. So all previous events up to a certain point are used to predict the next event. It turns out that to train these efficiently, it's not trivial. So in our paper, we design a new efficient training algorithm to basically speed up the learning of this model. But unfortunately, there is not enough time today to talk about this. So before going to the experiments, let me talk a little bit about scalability. So maybe the memory could be a concern, but actually it's not really a concern for scalability, since it's not a parameter, and we can just think of it as an additional feature vector for each node, which just changes over time. So basically, if we're doing learning at any time on the GPU, we only need the memory for nodes which are involved in a batch. So if you are doing graph sampling, so for instance, neighbor sampling as proposed by GraphSage, we just need the memory of a subset of nodes in GPU memory. And this means that our model is as scalable basically as GraphSage, so it can scale to very large graphs, even if we don't have this kind of experiments in the paper. So going to experiments and also being a bit aware of time. So we have experiments on 2 tasks, so future link prediction, edge prediction, and also dynamic node classification. So we evaluate on 3 data sets. Wikipedia is a data set of user editing Wikipedia pages, where we have the edges are when a user edits a page, and the edge features are basically an embedding of the text of the interaction. Reddit is a data set of users interacting with the subreddits, so posting to subreddits, where again the edge features are embedding of the text of the post. And Twitter is an embedding of users interacting with each other, so retweet replies, where again the embeddings are the features of the edges are embeddings of the text of the interaction. 2 scenarios: transductive, meaning the test set contains the same nodes already seen in the training set, and inductive, meaning completely new nodes that were not seen during training. We compare to some classic stat model for static graphs, so GraphSage, DeepWalk, and so on, and also to state-of-the-art models for dynamic graphs. And we outperform other models in all data sets for future edge prediction and also for dynamic node classification. Here, the task is basically it's a binary classification task to predict whether a user was banned at a specific time. And Wikipedia people are banned because they post, I guess, rubbish, and on Reddit, if they're spammy, they get banned. So we want to predict that based on the interactions they have. And we obtain very good results here. We also in the paper have a detailed ablation study where we try different variations of our model, trying different implementation of the modules. And basically, we also showed that we are faster, more accurate than other approaches. So this is time, and this is kind of accuracy. And we also kind of prove here that having both the memory and also the GNN, the graph embedding module, both are very, very important components that you can't just do with one. And the graph attention performs best compared to, for instance, just doing a sum of the neighborhood vectors. Probably because it's important to know when things happen and to be able to attend to all these sum events. So something we don't do, but is also very interesting, is, as I was mentioning, predict when things will happen. And it's kind of a qualitative different questions that really, you try to predict when things will happen, or how many things will happen in the next 30 or 60 minutes, as in this case, how many retweets will happen. And to answer these kind of questions, you really need a decoder which makes use of temporal point processes, which is a stochastic model which is used to handle basically sequences, events happening in continuous time. And this paper, DIREP, basically does that. So have a look at that if you're interested in this. So wrapping up some interesting directions. We definitely need more benchmark data sets for dynamic graphs. So I think we have done a great work in static graphs with OGB to really have more interesting data sets. And in dynamic graphs, we're not there yet. So if you have ideas for interesting data set or applications, that would be amazing. Possibly method extensions, possibly scaling it further, combining it with the graph sampling literature, even though it's not trivial. And then all the applications, so social network, biology, finance, and I guess possibly more. So to sum up, we've seen that the dynamic graphs are very common, but interestingly, they receive little attention so far. We propose a model which is kind of a general encoder for dynamic graphs, which obtain very good results, combined with also an efficient algorithm for fast training. And we also have a kind of a detailed ablation study to show the importance of the difference model. And with this, I will like to open it up for questions, and follow me on Twitter if you want to hear regularly about dynamic graphs or GNN in general. And thank you again.
Thank you very much, Emma. for the nice talk. So we have time for some questions. So let me start myself. What can be said about cases where you have periodic temporal signals? So, for example, in case of social networks, there might be some behavior, like, for example, daily and night differences, or maybe something that has recurrence on a weekly basis. How would you model this kind of process with dynamic graph CNNs, with temporal graph?
Yeah, sure. Yeah, very good question. So something I didn't mention was that in basically when we have messages, or basically every time we use the timestamps, using the timestamp itself it turns out that it doesn't work very well. So for instance, it's very hard to find these periodic, hard for the model to learn these periodic patterns. So there's been kind of a lot of work to in kind of figuring out how to encode or how to represent timestamps. And so for instance, there is two papers that do something very similar. So both one is called time to back, so providing kind of trying to learn an embedding for timestamps, and also the TGAT paper, which I mentioned here, also ends up doing something similar. But it turns out that from some experiments that I did, it's still kind of very hard to learn good embeddings that are able to capture these periodic patterns. So I think that's a very interesting direction. It may be solved to some degree, but I think not totally. Another opportunity, I guess, is also to use continuous time models. So for instance, neural ODE in combination with RNN. So there's been also a line of work there. And I guess that can also handle these kind of issues.
Thank you. And a question from the website. Well, very great talk. TGN is very efficient in inference. How about the comparison of the training complexity between different methods, TGN and TGAT? And also, do you know the recent work on causal anonymous walks? And how does it compare to TGN? So probably two questions in one.
Yeah, so for the paper, I have to say that I've seen it and it's my reading list, but I haven't got around to look at it yet, unfortunately, so I can't really comment on that. The other question was for the efficiency. So since we still have the memory, TGN kind of has to still do the sequential updates, which slows down a little bit. However, it turns out that it's still faster than TGAT, because the memory, as I'm, this last point here, the memory, since it's implicitly contains information from the graph, it allows us to only use then one graph attention layer, whereas TGAT, to achieve good performance, basically really needs two attention layer, which, given that is doing sampling, slows things down, really slows things down. Whereas basically, if we go for, this is one layer, this two layer, the performance is almost identical. So we can do things very well. Anyway, and here they also need more neighbors, again, because they don't have the memory. So I think theoretically, TGAT is more efficient, but to obtain good performances, we are more efficient.
Okay, another question. For social network, you would also look into personalization. How can you do this for temporal graphs?
So I guess personalization comes from we are learning a different embeddings for each node. So you can think, let's say we're recommending tweets to users. So you're gonna have a graph with both tweets and users, and you're gonna learn different embeddings for each user and for each tweet. So each user will have personalized recommendation just by the fact that it has a different embedding. And so when we have, let's say our decoder, which takes, let's say, a user and a tweet to decide whether to recommend the tweet, it's going to depend on the user embedding, and so it's going to be personalized, I guess.
I see. And another question: does the dynamic graph model based on a subgraph based node embeddings to be aggregated based on attention? Wait a second, I need to understand.
Yeah, maybe if we again.
Dynamic graph model be based on a subgraph based node embeddings to be aggregated based on attention. Also, can it help with sequentiality?
So if we have subgraph based node embeddings, so this is one thing.
Yeah.
So we have some node embeddings based on subgraphs, and then we use this in doing our aggregation. So I guess, yeah, if we pre-compute some node embeddings, which I'm not sure what subgraph node embeddings are, but I guess they are some variation of deep walk or node to vec. I think, you know, I haven't tried this, but I guess they could or they could not. Hard to say until you try.
I see. And maybe, well, another question. So before the break, basically there are several approaches that try to look beyond message passing, beyond nodes and edges, looking at higher order structures such as simplicial complexes and graph motifs. What, in your opinion, is the way to combine dynamic or temporal graph networks with these higher order structures?
Yeah, I mean, I think they can be very much related in the sense that when I say here, I say, okay, now we do graph attention or we do a GNN, right? But then there is the question of even what is the graph that you want to do the GNN on? Because the trivial solution is to just have a graph which is all the edges that you've seen so far, all the interactions. But then, you know, if an edge gets deleted, I guess you remove that edge from the graph. But then in general, I think you can think of using the sequence of interactions. So also this is an interesting direction to kind of learn what is the right graph to use. So all that direction could be integrated here of, you know, using a different graph from the input graph, but also using higher order structures, using motifs. And also, yeah, there is some interesting work on temporal motifs, which also look at when things happen. So for instance, if there is a triangle that was in a particular order of time, gives you some different information. So I think they can very much be combined.